All right, welcome back to the final week of lectures, anyway, in the HoTTEST summer school. So we'll continue with some colloquia that I'll tell you a bit more about in the future. So today we're very happy to welcome back Egbert Rijke, who's going to continue his series on some topics that he'll tell us about now. Egbert, take us away.
Yeah, thank you so much, Emily. So I want to begin by briefly recalling what we did last time on Wednesday. So we introduced propositional truncations, and we did that by describing first the universal property of the propositional truncations, and then implementing a specific propositional truncation. And we noticed also that the Curry-Howard isomorphism was not always the most accurate way to translate concepts from language or from mathematics into type theory. For example, we saw that if you use Curry-Howard to say what surjectivity means, then you get a section of your map, and this was too strong. And we saw that if you want to express finiteness without propositional truncations, then accidentally you've equipped your type with linear order. So we ended up with the concept of finite linear order instead of arbitrary finite types. And the fix for all of those issues was to use propositional truncations. And today I'm going to talk about the Univalence Axiom, which doesn't necessarily have so much to do with propositional truncations, but we are going to use the way we defined finite types to discover some maybe unexpected things about the Univalence Axiom. And then on Friday in my last lecture, we're gonna put it all together and try to use univalence in everyday concept from combinatorics. So that's the plan. So let me just go to today's page. I'll just continue the same notes as I did on Wednesday. So let's start with a definition. Definition. Consider two types, A and B, in the same universe U. Then we define a map, and it goes from the type of identifications of A and B, and it lands in the type of equivalences from A to B. Such a map we can always define whenever we have here on the right-hand side a reflexive relation. Then we can do path induction on the identifications and use reflexivity over here to say where ref should go. So in this case, we know that equivalences are that's a reflexive relation because we have the identity equivalence always. So we can define this map, and let's also give it a name. It's the equivalence obtained from an equality. Oops. This is the name of that map that I use in the book. And we just simply define it by equiv of refl is defined to be the identity equivalence. Okay, so you all know by now how to use path induction to make that definition precise. And here I kind of just define it with pattern matching, and either way the definition is okay. Okay, so what is the univalence axiom about? It's gonna tell us that equivalent types are equal. Oops. So it is a characterization of the identity type of the universe. And the thing that it says is that this particular map here is an equivalence. So let's see where we are. The univalence axiom asserts, asserts that the map equiv ec from A equals B. Where are we? From A equals, to A equivalent B, that this map is an equivalence for all A, B, and U. So if we say that U is a univalent universe, then we mean that this map here is an equivalence. And usually in type theory, we just assume that or if we want to assume univalence, we usually assume that all universes are univalent. So that's what we will do. And let's begin with a few remarks about this axiom, because it's of course nice to have a characterization of the identity type of the universe, but what exactly does it do? So let's have some remarks. First one is just by the fact that it's a characterization of an identity type, we know by the fundamental theorem of identity types that the total space of all equivalences is going to be contractible. By the fundamental theorem of identity types, it follows that the sigma type of all B and U that are equivalent to A, that this is contractible for all A and U. Oops. Where's my pen? Okay. So for those of you who don't recall the fundamental theorem of identity types, it was the theorem that says that if you have a candidate characterization of your identity type, so in this case it's A is equivalent to B, then the canonical map that goes from the equalities into the type family that you use to characterize the identity type with, that this is an equivalence if and only if the total space is contractible. So the first thing that we observe is if we assume univalence, then it must be the case that the total space of all equivalences is contractible. Another thing, which I'm not going to write down, that was in the fundamental theorem of identity types, was that you can do an induction principle for the type family that you characterize the identity type with. So in this case, equivalences. And this induction principle is just like the induction principle for the identity type. So in this case, it's a principle called equivalence induction. And it says that if you want to prove something for all equivalences, then it suffices to prove that fact for the identity equivalence. So if you want to know more about it, this is explained in my book, but I'm not going to do that now because we have a lot of other things to do today. Let's continue. There's also the slogan version of univalence. So often people give the slogan version of univalence. And this one simply states that A, the type of identities from A to B is equivalent to type of equivalences from A to B. And now I have a question for you. Question is this statement equivalent to univalence or not? So maybe in the chat you can let me know whether you think it is equivalent to univalence or not equivalent to univalence. I'm gonna have a look in the chat. Do people have opinions on this? It doesn't say that REFL goes to the identity type, that's right. So perhaps it's not equivalent. I guess no, but yeah, right. So it's hard to pin down. So you get a feeling that, okay, there's no reason why REFL should go to the identity equivalence. But still, it turns out to be the case that you can prove the univalence axiom as stated in the definition from this principle. So let's see how that goes. Someone notices that they should use the fundamental theorem of identity types. This is very good. You should always use the fundamental theorem of identity types. I was glad to see that. Okay, so yeah, we are going to use exactly that. So if we have the answer, so if we have such a family of equivalences for every A and B, so we just know this, and we don't know that it's a REFL goes to identity function. But then we still obtain that sigma B in U A equals B, that this type is equivalent to sigma B in U A is equivalent to B. If we have such a family of equivalences indexed by A and B, then it induces also an equivalence on the total space. That is something that's always true. But once you have this equivalence, now you observe that this is always contractible. So by having this equivalence, we know that the total space of all equivalences from A to B is contractible. And now we can use the fundamental theorem of identity type to conclude that this map must be also an equivalence. So this map might not be the same map as the underlying map of these equivalences, but we can still use these equivalences to prove that equiv egg this map that we defined here, that this must be an equivalence as soon as there's some equivalence from the identity type to A is equivalent to B. Okay, very good. Oh, I'm using trickery. I'm sorry, Emily. So if you want to know the exact statement of the fundamental theorem of identity types that that I'm using here, you have to refer to section 11 of my book, and that's the statement that I'm using. Yeah, with that we can go back and forth. All right. So the slogan version is very good. It's just a fine statement of univalence, but you should know that when people say univalence, and even if they mention this, actually the definition of the univalence axiom is that this canonical map is a family of equivalences. This is how Voevodsky defined it. So that's what it means. Okay. One more remark. Oh, I should also, of course, say before I forget, univalence. Oops, that is not a U. No, it is kind of a U. Is due to Voevodsky. Voevodsky. He invented this axiom around 2009, I believe. That's the first written account that I can think of is from that time. When he came up with this, he of course wanted to know also whether assuming the univalence axiom is consistent. So he made a model of type theory using consimplicial sets, where he was able to interpret all the constructors of type theory and prove that the univalence axiom holds. So it had at least one model, and therefore it was consistent. And then much later, around 2015 or 16, I believe, people came with a constructive model of the univalence axiom using cubical sets, where they were able to avoid any uses of axiom of choice that were present in the simplicial model, and even better, turn it into a programming language that is now cubical ACTA. So you can actually program with univalence, and how to do that is of course the topic of Anders's lectures. They are ongoing, not only did Voevodsky prove that univalence is consistent, he also proved something very funny, that univalence implies function. Oops, did I write a U here? Not sure. Extensionality. Oops. Let's erase that. Function. And this this also, I'm not going to prove it right now. It's a nice result, of course, that you can prove that it implies function extensionality. But we are going to focus on other things. And we just assume function extensionality. But if you want to know how that proof goes, then it's in section 17.2 of my book. What I do want to talk about is propositional extensionality. So propositional extensionality. This is a very important principle that even in some systems that don't assume the full univalence axiom, they still assume univalence for a proposition, and that's what propositional extensionality is. It says that equivalent propositions are equal, and this, for example, they assume this in the lean proof assistant also. So even in type theories where not full univalence is assumed, they still have this instance of univalence. Let's go to my notes. See what I'm talking about. Okay. So let's first recall that the type of all propositions in U, so now I'm gonna write the U here, is defined to be sigma x in U is prop x. And I think that at some point in your exercises, you must have shown that this is a proposition itself. What that implies is that if we look at the projection map PR1 from prop in U down to U, so it's going to take a pair of a type X with a proof that it's a proposition and just returns the type, that this is an embedding. And if you need to recall what an embedding is a map. So let's say i.e. the action on paths of PR1 for this particular PR1, not in general. This goes from P equals Q to PR1, P equals PR. I'm messing this up again, sorry. Let's just put that all on a new line. Okay. So this map PR1, which goes from P equals Q to PR1, P equals PR1 Q. This map is an equivalence for this projection map. So we can use that now because here we have an equality between propositions, but here on this side we have an equality between types, and we know that equality between types by univalence is equivalent to equivalence. So let's do a little calculation now. So if we start with two propositions P and Q, then we can write this is equivalent to PR1 P equals PR1 Q. This now is equivalent to, PR1 P is equivalent to PR1 Q, and we can even go one more step because we know that a map between propositions is an equivalence if and only if there's a map back. So the type of equivalences between propositions is equivalent to the type of logical equivalences. So this is the same thing as PR1 P if and only if PR1 Q. Okay. And usually when we have a proposition P, then we would also write P for the underlying type. So we can kind of say here that this is by convention just P if and only if Q. So here it is by convention. Because we usually don't write the projections explicitly. Let me just put there quotation marks also. But this is usually how you see it. The type of equalities between two propositions is equivalent to the type of logical equivalences between them. And it follows from univalence. So the univalence axiom is used here. Okay, so from all of this, we get a theorem, which is a theorem of propositional extensionality. Okay. For any P and Q, oops. See, I'm so not good at writing. I have the kind of tablet that doesn't have a screen. So for any P and Q, we have this map, the map from equalities. Sorry, this is an E. That takes P equals Q to P if and only if Q. And this map is an equivalence. That's a theorem. And it goes kind of by the reasoning. So by the reasoning that we just showed, we have some equivalence between these two types. But by the fundamental theorem again, it shows that the total space of all of these types ranging over Q, that's contractible, and then this this map here must be an equivalence. So so we proved it. And this has a very nice corollary. Let's write it here. Corollary. Consider two subtypes, P and Q from A to prop. Then P equals Q is equivalent to, for every A in A, P of A if and only if Q of A. So what is this saying? It's saying that the type of identifications of, so two subtypes are equal if and only if they contain exactly the same elements. That's what this is saying. And this is, of course, completely natural. So let's give the proof. Again, by the fundamental theorem, we are going to show that sigma Q from A to prop, and now for every A in A, PA QA we want to show that this here is contractible. Okay, but we know by the type theoretic axiom of choice that this is equivalent to, for every A in A, there is a proposition Q such that P of A holds if and only if Q holds. And now we observe that by the previous theorem, propositional extensionality, this type here is contractible. So this becomes a product of contractible types, which is by weak function extensionality, it is contractible. So that means that this total space here is contractible. And then by the fundamental theorem, we conclude that a type of identifications of two subtypes is equivalent to this type. Okay. This is a good moment to ask questions, if there are any. Why did we even need to introduce projections? Well, it's because prop is defined as this sigma type. That's why we an element of type prop is not just a type. It is a type together with a proof that it is a proposition. And then you use projection out of the sigma type to get your underlying type. So that's why. Are there any more questions? If not, then I will carry on. Okay, so the next thing we want to show using univalence is that the type of subtypes of A is equivalent to the type of embeddings into A. So this, of course, is also very familiar from set theory that that there are two ways, two equivalent ways to describe a subtype or subset of a set. One is by specifying a predicate of on the elements of that set, and the other one is to describe an inclusion from another set. And those are two equally good ways to describe a subset, and it's exactly the same in type theory. So now the types are not sets, but we can still prove that the type of subtypes of a type A is equivalent to the type of all types equipped with an embedding from X into A. And just as a remark, this here, this equivalence wouldn't be true if you would use injective maps instead of embeddings. So you need really that the action on paths is an equivalence. Yeah, maybe you recall that a map is an embedding if and only if the fibers are propositions. That is going to play a role, as we see in this equivalence. But that's not always true for injective maps. Okay, but actually what we're going to do is we're going to prove something more general than this. Let's make a theorem. This is something that that comes back over and over again if you live in a univalent world. Consider a type A. Then we have an equivalence that goes from the type of all type families over A to the type of all X in U. And now we don't need to have embeddings, but we can have ordinary maps into A. So this is saying here that to describe a type family, it's equivalent to describe a map into A. So let's give the maps back and forth. We actually already know them. So let's define phi in the forward direction. So oops. So if I assume that I have a type family B, then maybe you can help me in the chat. How can I define from a type family B? So here's my B. How can I define a type and a map into A? So let's open the chat. Do you have any ideas? Doesn't seem like the chat has any ideas on this. Okay. Ah, there is someone. Yeah, sigma type. Definitely. And then the map is gonna be, I'm sure you're gonna say that it's gonna be the projection. So here we have to define a pair, sigma x in A B of x. And then the map from sigma into A, this can really only be one thing. It's going to be projection. And let me call this thing here. Oops, sorry. Right. Okay. Let me call this thing psi because my notes say that it's called psi. And I will confuse myself. Okay. And now we have to define also phi using a type and a map into A. Oops, this is colon equals, of course. And given a map into A, a family over A that we get from it is the fiber of F. So this is a type family. Okay, so now the question is, why is this an equivalence? We're going to use univalence to prove this, but we are going to need some lemmas. But let's look at the two cases. Let's say we want to prove that phi composed with psi at a type family B equals B. In order to prove such an equality, we need to know what is equality in A arrow U, and the type of oh, sorry. A arrow U, question mark. So we're gonna prove a little lemma. And the lemma says that if I have let B and C be two type families over A, then B equals C is equivalent to, for every A in A, B A is equivalent to C A. It's the same reasoning that we just saw for propositions, but more generally. so it's an application of the fundamental theorem of identity types, and since that is so important, and I really would like you to master this, I'm just going to show it again. So we have to show that sigma C from A to U for every A in A, B A is equivalent to CA. You want to show that this is contractible. What you observe is by the axiom of the type theoretic principle of choice. You distribute the pi out of the sigma. Then you get sigma C in U. And now it's B A is equivalent to C. And we notice that this one is contractible. So it's a product of contractible types, therefore it must be contractible. And that's why we have this equivalence. Okay. So what we're really after here is this equation. So this lemma now says that it suffices to prove, to prove this for every A in A, to prove an equivalence. So we wanna now show that phi of psi of B evaluated at A is equivalent to B of A. This is now the goal. Now we have to remember what is psi of B, that's the total space with the projection. So this here is by definition, it is the fiber of PR1 of the projection map from B into A. And you all did this exercise, I assume, that this fiber is always equivalent to B of A. And if you didn't do this exercise, it is number 10.7 in the book. So then you can do it, but it constructs this equivalence. Okay, and we have now shown that psi is right inverse of phi, and there's one more case remaining, and this is that psi composites phi is an equivalent is equal to XF. Okay, so that why is this true? And here the equality is in this type here. The equality is in the sigma type of all x and u's equipped with a map from x to A. So again, we are going to characterize the identity type of this type. Yeah, this is probably the most important thing that I have to say to you during my all my 3 lectures, is that if you're working in type theory and you have some type that you're interested in, so now in this case we're interested in those 2 types, like almost guaranteed it is that you want to know something about the quality of this type. So go ahead and characterize it using the fundamental theorem of identity type. So this should just be standard. So we're going to do that now. So lemma, let XF and YG be elements of type sigma. Let me now write Z in U, Z arrow A. Then the type XF equals Y, sorry, not Z, G. This is equivalent to the type of all. Well, okay, so first you have to say what is equality from X to Y? Well, that's equality of types. So we can say this must be an equivalence from X to Y. And if you have an equivalence from X to Y, then you can draw maybe a little triangle A, and here we have F, and here we have G, and if we already have this equivalence, now we can ask that that this triangle here should commute. So that's saying that F is G composed with E. Okay, so now the claim is that that for XF and YG to be equal, it's equivalent to have an equivalence from X to Y and a homotopy from F to G composed with E. And again, we are going to prove this in our favorite way. So let's consider this sigma type. Sigma Y in U, sigma G from Y to A, sigma E from X to Y, and now F is homotopic to G composed E. So we want to show that this is contractible. The first two components are, of course, the type of Y and G. And the second two components, that's this type. So I already did some reassociating, but not too much, because I'm going to do some more now. So now we notice that we can swap this second sigma and the third sigma. Sigma Y in U, sigma E from X equivalent to Y. Now we have sigma G from Y to A, and then F is homotopic to G composed with E. And here we notice that this here is, of course, contractible, and the center of contraction is X comma id. So we are going to use that center of contraction and contract this out. And that will give us an equivalence here to this type, where we take X for Y and the identity function for E. Okay, so we get sigma G from X to A, and now F is homotopic to G composed with the identity function. Okay, so we don't have to write that down. But now we remember that by function extensionality, the type of homotopies between functions is equivalent to the type of identifications between functions. So this total space is also contractible. So this is equivalent to the unit type. And that's why the total space of this type here on the right-hand side is contractible, and that's why that you can use that to characterize the identity type of these pairs. And now we can finally prove that psi of phi of xf is xf. Okay, so let's do that. Psi of phi of xf. So phi of xf is the fiber of f, and then psi is the total space. So here we have sigma sigma a in a fib f a, and then the second component is the first projection. It's always for psi. And we want to show that this here is the same as xf. So what we want to do, and we're going to draw it here, is to construct a commuting triangle. I'm going to construct it in the other direction, actually. Sigma a in a fib f a. and A. And here we have F. Here, of course, we have the projection map. And this map here, it takes a little x, and it goes then to f of x. Oops, that's an x, not a star. Sorry. And then the pair x comma ruffle, which is in the fiber of f of x. And in my lecture on Wednesday, we saw that this map is an equivalence. And of course, if you go around from x down here with f, or you go first with this map and then you project out, well, we notice that the first component is f of x. So this triangle here commutes. And that's exactly what we needed to do to construct this equality, is to construct such a commuting triangle. That's what we've proven in our lemma. So this completes now the proof of the theorem. And let's just recall what the theorem says. It says that type families over A are equivalently described by maps into A. And of course, also a map into A is an embedding if and only if its fibers are propositions. So we can just read off from how we proved this this theorem that that the type of subtypes of A is the same thing or is equivalent to the type of embeddings into A. Okay, this is another good moment to ask questions, if there are any. Oh, there are not even open questions. Okay, well then I'll just continue. Okay. So this theorem that we just proved, sometimes people say that that the universe is an object classifier, and when they say that, they refer to this theorem. But I think you don't really need to know at this stage in the course what an object classifier is. Okay. So right. So now during this course, we have often said that that the law of excluded middle doesn't hold for all types, but only for propositions. And that the axiom of choice doesn't hold for all types, but only for sets. And I mean, that it's only consistent for sets and it's inconsistent for other types. That's what I mean. So now in the last half hour of this lecture, I'm gonna prove all the relevant facts for that. So let's recall from last lecture that BSN, that this is the type of all n element types. So this is sigma x in U, and then merely fin n is equivalent to x. Okay. And by the univalence axiom, so now I'm all right. I'm going to show this for n equals 2, but still, no, I can just yeah. So we know that that this here is a proposition. So BSN is a subtype of the universe. So in other words, the projection map from BSN into the universe, PR1, that this is an embedding. So in other words, that x equals y in BSN, this is equivalent to x is equivalent to y. And this is the reason why this type is called BSN, because it follows also that fin n equals fin n is equivalent to fin n is equivalent to fin n. And here on this side, we have exactly the permutations on an n element set. So what we have here is that that the loop space of BSN is the permutation group on n elements, and that's why we use this name for BSN. Okay. But let's zoom in a bit more on BS2, because BS2 is very, very interesting. Okay. Let's first prove that, let's prove proposition that sigma x in BS2 x is contractible. So what is this saying? It is saying that the groupoid of all two element types equipped with a point, that is a contractible groupoid. And of course, the morphisms in this groupoid should be base point preserving. So how do we prove this? Well, we already know that so basically this is going to be contractible if and only if the map from fin 2 to x to x is an equivalence. But we know by univalence that only holds if and only if the type of equivalences from fin 2 to x going down into x is an equivalence. And here we can take a particular one. We can take evaluation map at 0. So here's the claim. This is an equivalence. And if we prove that, then of course it's going to follow that the total space of pointed two element types is contractible. Because if we have such an equivalence, then it's going to induce an equivalence on total spaces. This total space is contractible, so the total space of this one will be contractible. But now, note something very important. Being an equivalence is a property, we made a big deal about it that being an equivalence should be a property, but we haven't used it so much, and here actually we are going to use that being an equivalence is a property to prove something, namely to prove this fact. And we have something, namely that fin 2 is equivalent to x, because x is assumed to be in BS2, or maybe it should be equals here, but it doesn't matter. So this is a full stop. We have some hypothesis of this this type, and since we are proving a property, we can use now the universal property of the propositional truncation that we saw last week. So we may assume that fin2 is equivalent to x. Okay, and now this is going to be very nice, because it follows, so it suffices to show, because x is assumed to be equivalent to fin2, that the evaluation map from fin2 to fin2, this evaluation map, evaluation at 0, that this is an equivalence. Oops. Okay, I'm gonna just tell you how to get back. But to get back, we must select two equivalences from fin2 to itself. We map 0 to the identity function equivalence, and we map 1 to the successor equivalence. And of course, there are no more. So I'm sure that you all are by now very capable of completing this proof from here. So I'm not gonna do that. It might be in the exercises for today's lecture. Anyway, you all know how to do it. Okay, so we saw now that that the type of pointed to element types is contractible. Are there any questions about this? If not, I will carry on. Oops. There's a corollary. So there's a reason why I was interested in this. And the corollary says that there is no dependent function. Oops, did I just write too much? Dependent, yes. There's no dependent function that takes a two-element type and returns an element. So this may seem strange to you, because two-element types have two elements, and why should I not be able to pick an element? But we can now prove that there cannot be such a function. If there is such a function, we can construct an element of the empty type. And the reason is proof. Well, we just saw that fin2 equals x is equivalent to x. So if we have a section here, bs2x, well, we surely know that this here is equivalent to, for every x, bs2, and then an equality from fin2 to x. But if you can construct this, this is exactly a contraction in the type bs2. So if we have a homotopy here, then we would obtain the pair fin2, h of type is counter bs2, and there surely cannot be any element of type is counter bs2, because we know that the identity type of bs2 can have two elements. It's not contractible. Two-element types are certainly not contractible. But we also know that all contractible types must have contractible identity types. So So BS2 is not contractible. We know that from its characterization of identity types. And that's why we cannot have such a section. Is that clear? Okay. Now let's have more corollaries. Corollary. There is no dependent function for every x in U. If x is inhabited, then we can construct an element of x. So this principle, if it holds, is called global choice, and also it is inconsistent. Oops. With univalence. Some of you may know that that the lean proof assistant, they assume global choice. So their system is not consistent with univalence. They also assume that every type is a set, of course, which is false for us. But yeah, let's see why global choice cannot hold. Well, suppose we have such a function h, then we can restrict h to for every x in BS2, merely x to x. So now we restricted h to the two element types, but surely the two element types are all inhabited. We might not be able to construct elements of them, but we are surely able to prove that they are inhabited in this sense. So we observe, since they are all inhabited, that this type here is equivalent to for every x in BS2 x, and we just saw that this cannot hold. So the reasoning here is, if there was a global choice function, then we could restrict it to BS2. But if we did that, then we would construct an element of arbitrary two-element type, and that's impossible. Let's see, are there any? Okay, so BS2 is the type of two-element types. And yes, and see if Javier wrote the correct definition. Yeah. And if you, I don't know if this is helpful to you, but for some people it is. It's helpful to think of BS2 as the groupoid of all two-element sets. If you know what categories are and what groupoids are, this is a nice groupoid, and it's not a contractible groupoid because it has non-trivial automorphisms, and that's basically a good model for what BS2 is. Okay. So if we cannot assume global choice, we still may want to assume the axiom of choice. The only thing is that we have to be a little bit more careful. So we can also not say restrict global choice to sets, because the two-element types are all sets. So if you restrict to sets, then it's still going to be inconsistent. So global choice is completely out of the window, but the axiom of choice is fine. So I'm going to make a definition. we're usually not assuming the axiom of choice, but the correct axiom of choice, the axiom of choice, the one that is actually an axiom and not something that is just true. This asserts that for every set, so it's important that this is a set, and every family B of sets, again important, over A, we have a function like this. So if for every A in A, B of A is inhabited, so let's put parentheses around this. So if they are all inhabited, then there merely exists, oops, how did that happen? I never used such fancy features. A section of B. So this is the axiom of choice. If you can show that each B of A is inhabited, then then you can merely construct a section. And we can immediately see that if we didn't assume that A is a set, then we can construct a counterexample using using the BS2 again. So now if we take A to be BS2 and B of A to be A itself, so X in BS2 and then merely X. So of course, every two-element type is inhabited, but we have shown that this type here is empty. So then it doesn't matter if you take the propositional truncation, it will remain empty. Is BS2 a universe? It is a subtype of the universe. Let me show the definition again because people apparently missed it. Okay, here is the definition of BSN. It is the type of all types in U such that merely fin n is equivalent to X. So because this is a proposition that's a subtype of the universe, and what that means is that projection map from BSN into U is an embedding. Hope that is clear now. And indeed, you can also say that it's a path component of the universe. We didn't really talk about connected components of types, but I'm sure that Jarl will be very happy to explain that tomorrow in his exercise session. What connected types is. He is one of the experts. Great. Let's see. I have 15 minutes. So actually, I'm gonna stop slightly short, but not yet. But I want to talk about the law of excluded middle, and then we will wrap up for today. So now there's another corollary. There is no dependent function that says for every X in U is decidable X. And remember that this just means that X plus not X. So this is a coproduct of the type X with type of functions from X into the empty type. So here again, how do we prove that there can be no such function? Well, we kind of know the drill right now. If there is such a function, then we can look at the type of all X in BS2. That's why BS2 is so nice. It's so simple. And then let me write out x plus not x. Okay. So if we had this, then actually we can simplify this a little bit so that it's just type of sections of BS2 again. Because we know that if x is in BS2, then we know that it's inhabited. And if it is inhabited, then we know that it's not empty. But if one of your components of your coproduct is empty, so here we're showing that the type of negations of x is empty. If one of the components of your coproduct is empty, then the coproduct is just what's on the other side. So that's the unit law of coproducts, BS2X, and of course we already saw that there can be no such function. So that means that that there can be no function of this kind. Okay. So here, what we are seeing that is even for finite sets, we cannot decide whether it has an element or not. What we can decide is whether they are inhabited, but we cannot either construct an element or show that it's empty. That's what we cannot do. So if we want to assume the law of excluded middle, so it is possible, but it's not for all types. LEM asserts that for all P in prop, we have either P or not P. And it is a little exercise that you can show that this is equivalent to P plus not P. And the reason that these are equivalent, so if you recall from last lecture, we defined this to be P plus not P, but the propositional truncation of that. The reason why we have an equivalence like this is that these cases are mutually exclusive. If there's an element in the left-hand side, then the right-hand side must be empty, and therefore the coproduct was equivalent. And if it was on the right-hand side, then the left-hand side must have been empty, so it was still a proposition. So the law of excluded middle asserts that for every proposition, P or not P holds. So let me erase some of this mess. Oops. And so it holds. Let me just wrap up. What we saw that if you assume univalence, then suddenly you have lots of options to characterize identity types. We saw many instances of many applications of the fundamental theorem of identity types today. And also we saw that if you assume univalence, then you must be a little bit careful about what classical principles you assume and mostly how you assume them. Because we saw that global choice is just outright false. And also the law of excluded middle, if you're not careful, it's gonna give you a false statement, or univalence will imply that it's false. So so the correct way to assume law of excluded middle is to restrict it to propositions. And the correct way to assume the axiom of choice is to restrict it to sets, which is also very natural, given that the axiom of choice has been for 100 years an axiom about sets. So it's not really a surprise that you have to make some restriction. Okay, that's it for today. We have some extra time for questions.
Great. Well, let's start by thanking Egbert for another wonderful lecture. So.
My pleasure.
All right. So if you want to ask a question right now, feel free to raise your hand. We can recognize you. Otherwise, we'll turn off the recording and have an opportunity for questions. Or if any of the TAs want to jump in and voice some of the questions you all have been answering in the Q&A, we'd be happy to hear about them.
Oh, there's a question, is there like a generalization for the axiom of choice that you can assume for types that are not sets? There are some proposals for it. In the HoTT book, there's an exercise that asks that if a product of k-connected types is again k-connected, I think that's the analog of higher axiom of choice. But I'm not sure if people really have investigated those questions very seriously. So it's mostly open territory. Of course, in topology, products of connected spaces are connected. But yeah. Barry, are you typing that up?
I was trying to remember. I think isn't in the simplicial model, isn't it consistent the axiom of choice for untruncated types? I think A still needs to be a set, but
yeah, okay. So you can assume that the type family B is not truncated. This is possible.
I believe that's correct. Yeah.
Yeah. I think it is interesting though, because I'm not sure if anything. Well, actually, I shouldn't even mention it because we haven't done truncations for anything other than propositional.
This one you can generalize. But yeah, the really a generalization of this to higher types would be that the product of connected types is connected. I think that's of highly connected types. Let me say it like that. Yeah. Cool.
Great. So let me stop the recording.
Yeah.
Thanks you all, and we'll see you in a few days.